Hello, my name is Johan Kaito. I am PhD on chemometric support engineer. To make it simple, chemometrics is a science of using mathematical, statistical and computer method in order to improve the extraction of relevant information obtained from analytical data. So, in our case, from Raman data. The objective of our support offering is to make this discipline accessible to all of our customers, even non-experts. That's why we assist them in building models by providing some guidance on chemometrics foundation, spectral analysis, on how to build robust chemometrics models for their processes. Chemometrics includes two types of multivariate data analysis techniques mainly used in bioprocessing applications. First, the exploratory analysis, such as PCA, standing for Principal Component Analysis, which is mainly used to explore and to describe a multivariate dataset, allowing the identification of trends and process trajectories. This is also a useful tool for the detection of outliers to check if something went wrong during the process that impacted the data. Second, the quantitative analysis, like partial least square regression, which is one of the most widely used quantitative methods in chemometrics to estimate and to quantify the Raman signature of various components in a given sample. This method gives statistical models which are key for the customer to move on to the monitoring step, which consists of obtaining real-time quantitative values of various metabolites from cell culture processes. It is essential to define a design space around one process when implementing Raman spectroscopy. The development of robust regression model having integrated some variabilities lead to better monitoring capabilities if the process changes during the spectral acquisitions. This is why process variabilities, especially biological and instrumental variabilities, need to be taken into account during the calibration step. Within the model space, there is the golden batch, which is a process that the customers want to reach. And the objective here is to add some variabilities in the experimental condition of the calibration batches in order to build the space around this golden batch. Here, we illustrate a process change, meaning that if you try to measure another process with experimental condition outside of the operability limits, then the model will not be able to monitor it with accuracy and consistency. Therefore, we generally recommend to perform at least 3 different batches containing more or less 15-20 samples per batch to start the calibration. One challenge of using Raman spectroscopy for measuring multiple analytes in cell cultures is that many of the metabolites are highly correlated between them. It is necessary to generate robust models by breaking this correlation, ensuring that the developed models are specific of the analyte of interest and therefore less influenced by the fluctuation in other components. This can be achieved through spiking of known concentration, for instance, to deconvolute the signal information. This is performed to increase the concentration ranges used for the calibration and to have significant changes in the spectra to be able to link the offline values with the spectral variation. This ensures that the model will be measuring the specific analyte and not infer based on a correlation with another metabolite.